So this lesson is part of the A-level chemistry crash course, which is a specific exam preparation course where we will look at essential concepts of chemistry. We will simplify it as much as possible so that you can really understand the essential concept in order to apply more easily to exam style questions, because the goal is really to have the knowledge, which is independent of the type of question that you will have, independent of any type of exercises. You need to have the knowledge so that you can apply to any type of questions, okay? Because that's chemistry. It's not so much about memory, it's about knowledge and how you're able to apply this knowledge. So this is the goal of this course. And today we will start with carbonyl compounds. You will see we will mash up different topics together. We will revise the essential concept from AS chemistry because these recur in all organic chemistry. Okay. In fact, today we will start, and actually one little point, why do I put all of the specification codes of all of exam boards? Because yes, of course, you will need some specific preparation for your exams. You need to get familiar with your exam board and so on. However, the concept is chemistry. It doesn't matter the exam board. Okay, so when it's common for all of the exam boards, you will benefit from practicing all of them. Okay. So the lessons are always, the layout is always the same, but you will find out more if you join the course. Today, we will look at the mechanisms because we will revise bonding shapes and forces of carbonyl compounds. We will predict the directivity of carbonyl compounds, not from memory, but from the knowledge, the chemistry knowledge. We will also have a look at mechanisms in general this time, because we will look at comparing nucleophilic addition-elimination and the nucleophilic addition mechanism, okay? And then we will look also at enantiomerics products in this reaction, okay? Then if you will join the course, you will have access to the rest of the lesson, okay? As I said, before you start, of course, you need to remember the essentials of bonding, shapes, and forces, but for today's lesson, I will revisit that as well. Essentials of organic chemistry, electrophile, nucleophile, curly hours, you need to make sure you know the basics. And then, well, oxidation of alcohols is not for having this short lesson. So the foundation concepts are important to understand and predict the reactivity of organic molecules. So what are the foundations and what are something that you always need to consider when you analyze a functional group? Bonding, forces, and shapes. So bonding. Let's look at the carbonyls here. This R group could be anything. It doesn't matter too much, okay? Because the focus is at the bond, the carbon double bond O. So bonding, we have a double covalent bond, okay? You know, dot and cross diagram, we have two pairs of electrons. It doesn't matter too much. What is important about the bonding and how can it be related to the mechanism is how these bonds form. Because we know that a sigma bond is formed, yeah, simply by the overlap of s orbitals or the side-on overlap of p orbitals. So it's very strong. It's important to remember. While the p orbital is a side-on overlap. It's useful to know that a side-on overlap, it's less strong than actual overlap. This is important because you will see this in mechanism. You need to be able to predict which bond will break first. And that's where you need to think about the strength. Forces doesn't affect directly. Actually, you know what? It does affect the mechanism because you have written here two dipoles. These dipoles are essential to understand the mechanism because you needed to identify nucleophile electrophile. We'll look at that in a moment. Anyway, for this carbonyl, we have London dispersion force, like any molecule, and dipole-dipole interaction because there is a difference in electronegativity between carbon and oxygen. This results in a polar bond. And then you will see what that's relevant for the mechanism. The shape. So we know that the focus is these carbonyl bonds. So we have 3 bond pairs. And remember that the double bond counts as a bond. Yeah, you need to look at if you don't want to, if the pair sounds confusing, you need to think about the region of electron density. In this case, you have 3. one double bond, and then two single bonds. So 3 bond pairs, there are no lone pairs around the carbon. This will give you a trigonal plane with an angle of 120 degrees, just to revise it. This is useful because in some, you could have tricky questions or some tricky explanations. Maybe your teacher is explaining it like that at school, I don't know. But during mechanisms, there could be a change in the shape of the molecule, or the shape of the molecule may affect the final product. That's why you need, whenever you do any analysis of any mechanism, you need to think about these things, because it will help you work out a mechanism if you don't know it or if you're not familiar. So let's think for a moment. Whenever you have to work out a mechanism, the first thing that you need to do is, well, apart from all of this analysis, but the resulting, of this analysis is you need to work out what's the electrophile, what's the nucleophile. Yeah, because like this, you will be able to write down the curly arrows. So if you look at your at the dipoles, you could think, well, the oxygen has a negative dipole, so it could react as a nucleophile. Remembering, nucleophile is a lone pair donor, while the carbon is delta positive, could be a lone pair acceptor, an electrophile. Remembering, nucleophile are attracted to positive, electrophile attracted to negative. But I want you to think about the basics of bonding. Oxygen only wants to have 2 bonds. So despite it has a negative dipole, it's a really small atom, okay? It doesn't really want any other bond. That's why when you have a carbonyl, you know that the reactive center is this electrophilic carbon. That is it. Okay, so this you can remember it, but you see how you can work it out by the basic knowledge of bonding. Let's look at the mechanism and how we can actually work it out. So I know it's a lot of text, but bear with me. We're going to look at step by step. So step 1, as we said, you have your molecule, whichever molecule it is. We're still looking at this general carbonyl. You write down the dipoles. You know that, again, the dipoles, why? Because you can look at the intermolecular forces. And second step, you identify the nucleophile and the electrophile. The nucleophile, in this case, it's something that is reacting with it. So you need to always look at what is the other molecule that is reacting with. And the electrophile, we know, is our center. Also, think logically, it cannot be the negative oxygen and the nucleophile reacting together, right? Basic, but still logic. So we always need to think about that. What you can do then is write down the first curly arrow, always independently of if you know the mechanism or not. Nucleophile always attracts the electrophile. Okay, so this, you know it, you can work out this part of the mechanism without any knowledge of the mechanism itself. Step 4, what's the consequence of that new bond? And here comes a bit of logic. Another one should break if the carbon has too many bonds. Which one? The weakest one. So think about what we said about the double bonds. We know that's going to be the weakest, not the double bond, but the pi bond is going to be the weakest one. Because here we have 3 sigma bonds, so they're not going to break. It's going to be the pi, the pi bond that breaks. Okay, but how can it break? Well, we know that oxygen can hold more charge. The reason of it is a little bit more complex, so I won't bother you with that too much in terms of orbitals, okay? But you just need to think logically where these electrons can go from the pi bond. Can only go into the oxygen, can't go between here, can't go between there. It doesn't make sense. So step 5, write down the intermediate and think what's next. So here's your intermediate. It's very important that you think about the charges. So movement of a pair of electrons. So there could be a charge after the gain or loss of electrons. Why is a charge? You really need to think about, well, there is a transfer of electrons somehow, because now these electrons that were belonging to the carbons, they're now on top of the oxygen, away from the carbon, okay? Which means that this has a negative charge. Carbon doesn't have a positive charge in this case because the nucleophile has given its electrons. If you struggle visualizing this, it's really, really useful. Write down dot and cross diagrams and think about how each of these movements, so each of these curly arrow affects the actual movement of electron in terms of dot and cross diagram. So really try that in case you have any doubt, or if you can't remember the this movement of electrons. Okay. Now, step 5, bear with me. Let's look at one portion of the screen at the time. Depends on what the carbonyl is reacting with. Now, we have this intermediate, isn't it? The oxygen with a negative charge, the carbon with the 2 groups, and then the nucleophile. So we have 2 possible mechanisms, and it depends on the molecule, on the substrate. If R is a good leaving group, if R is not a good leaving group. So a leaving group is a stable molecule, something that can exist on its own and it's pretty stable. If that is the case, these bonds will want to break. Okay, it don't need to think too much about the reason, but that's how it works. The double bond will reform because oxygen is really not happy like this. You need to think that, well, it's gonna want to become a neutral molecule. So this bond will rejoin so that this carbon bond and the leaving group is gone. The result would be the carbonyl with that nucleophile attached and a side product, that whatever leaving group we had with a negative charge. Once again, I hope you can visualize that the electrons are actually going onto this R group. If R is not a good leaving group and H plus is present, then the most likely thing to happen is that the negative oxygen will react with the H plus, forming now an alcohol. So here we've just seen 2 different mechanisms, addition-elimination and nucleophilic addition. So addition-elimination, notice that it's kind of a substitution, but occurs in 2 distinct, very distinct steps: the addition of the nucleophile and then the elimination of the leaving group. So you may ask, which molecules actually do that? Well, addition-elimination is where there is a leaving group. And you will see that because it's a molecule, remember, it's a molecule that is stable on its own. Chloride, the chloride ion, well, it's pretty happy to be on its own because there's going to be something else in the solution to react with and maybe forming a salt. And we know that energetically it's always highly favored. Or look at this. This is a whole big leaving group. Yeah. And how do I know that the leaving group, it's that the highlighted one? Well, because remember the focus of this reaction is the carbonyl. So it's a very reactive molecule, isn't it? So this is going to be the leaving group. This could also be, it's a carboxylic acid. Yeah. Well, think about how esters are formed. It's this exact mechanism. Yeah. Nucleophile. Yeah. With one of this to form, the ester. It all depends on what this nucleophile is, of course. For the nucleophilic addition, notice that we have carbon-carbon bond, very, very strong, we know that, and carbon-hydrogen bond, another very strong bond. So those are not leaving group, and this is the reason why the mechanism, it's different. And that's why you also know the reagents for this, that there must be some acid added after, okay? Because, well, and normally is added like as a last step. It really depends on the on what this nucleophile is. Okay, so we can have a lot of conversion between different groups, between different functional groups, and it can get very confusing. So remembering all of the reagents and so on. But the first step is really to understand the general mechanism, because then it doesn't matter what the nucleophile is, it can be any, you know how to work out the mechanism. There could be some extra step, there could be some intermediates, there could be more charges, but you can always work that out, because if you understand the movement of electrons, then you can also understand where the charges of these intermediates are. So looking at this mechanism, as you've seen, we have discussed the bonding. So these, the pi bond, why is important to know that that's the weakest one. Also, of course, the force is because we know that to work out the mechanism, we needed to know the positive and negative dipoles, but we haven't really thought about the shape. Why is the shape important? So I want you to notice something. We know that our carbonyl is planar. But if it's flat, Yeah, we drew this as a two-dimensional shape with the nucleophile attacking over here. Not really like that. So the nucleophile can attack. It has equal chances of attack above and below the plane or this planar molecule. Here, I don't know if you're noticing, I'm really saying some keywords that are the keywords that gives you mark in exam questions. It's planar or plane, equal chance of attack, equal probability from either side. Those are all the keywords that we need. So notice what happens. Let's see if you can visualize it because, well, there is a change in a stereochemistry. We go from a three bonds carbon to a 4 bonds carbon. So the nucleophile, if attacks above the plane, it will push down the oxygen. So the nucleophile will kind of stick out above. But if the nucleophile attacks below the plane, it would stick it up on the opposite side. As we know, the bonds, they want to arrange themselves as far as possible, right? That's why it takes a specific shape. Okay? Then, of course, it would be completing the mechanism. The important thing is that if there is equal probability, these two molecules, they're called enantiomers. Enantiomers are present, first of all, only if there is a chiral carbon. So only if these 4 bonds, they're different. So don't worry about, this is just very skeletal representation, but imagine these 4 bonds are all different from one another. One could be a hydrogen, the other one could be a CH3, the other one could be, in this case, oxygen, and the nucleophile maybe is different. If there is a chiral carbon, you would have enantiomers. And here we're talking about the stereoisomers, which are molecules that have same molecular, same structural formula, but different orientation in space. So notice, and if maybe you see this as well, there is a symmetry over here in between these these 2 planes. And these are mirror images, but they're not superimposable, as we know, like our hand, they're not superimposable mirror images. And this makes them different molecules. Okay, there is only one property that is different, which is what they do with the plane of polarized light. But this is in the topic of optical isomers. Okay, but of course, they have exactly the same structural molecular formula, so their properties are going to be pretty much the same. Okay, now it's your turn. I want you to think about, for each of this, do enantiomers form? We have a cyanide, which is a very good nucleophile in this case because it has a quite like it's a good intermediate to have so that we can change between different functional groups. It's also one of these nucleophiles that allows extending the carbon chain. But now I want you to think about that, and you can do the mechanism, or maybe you do that analysis of there is a living group, there is not a living group. What I want you to do is write down the products and then think if there are enantiomers that can be formed. I would suggest you to take 5 minutes for this, so you could pause the video and then play when you're ready to hear the solution. So I hope you had some time to practice this. Remember, you can always expand all of the exercises you do by drawing out the full mechanism. Okay, do the analysis that we did so far. Okay, but let's look at this in specific. We want to know if enantiomers formed. Well, the product of this will be, we know that there is no living group in this. We know also it's an aldehyde plus a cyanide. We will have the nucleophilic addition. So we will form these molecules. How do you know if there is a chiral center? You need to identify there are 4 different groups around. It's a skeletal formula, but remember there is a hydrogen there as well. So this is going to be chiral. Ketone. Yeah, we have this addition forming an alcohol. There is no chiral center because we have 2 of the same groups. Another ketone, but this time this ketone it's an asymmetric, so it will form a chiral center. Well, the last one, it's not. There is also a side product because look, this is a really good moving group. So we're gonna have two chiral centers formed. The important thing about that, remember that, as we said, that there is a equal chance of attack above and below the plane. This means that you're going to have the same chance of having this enantiomer and this, which means that it forms a racemic mixture. Now, the only difference, and here will be how you can distinguish between these enantiomers, because as we said, well, they're pretty much the same. So what do they have different? Well, they rotate the plane of polarized light in opposite direction. Okay, so I don't have a diagram right now with me, but imagine that plane of polarized light is just like light in one direction. Going through one enantiomer, it would rotate it in one direction. The other enantiomer would rotate it in the opposite direction by the same extent. So this is the only difference between the enantiomers. So you need to be able to explain why a racemic mixture is formed. But going one step back, you need to be able to work out the products and the type of mechanism. And I think all of this analysis is very useful. So the shapes, the bonding, and the forces. If you have any questions, let me know. Otherwise, I will show you why these can be useful. Like what is the point of this, of the keynotes about this? Well, here are some exam questions. We're not going to complete them now because if you want to have access to my summary notes and all of the questions, you will have to join the course privately. But look, describe how you can distinguish separate samples of two stereoisomers. Exactly what I said about the plane of polarized light. Or why the reaction mixture produces a racemic mixture. 3 marks, 3 easy marks, if you know how to say. Exactly what I said about the shape. So you could give it a go to explain it, maybe not in your own word, because it's very, the keywords are planar, attack of the nucleophile, equal probability, and of course, attack above and below the plane. 3 easy marks. Okay. Then if we have an isomer compound that it does not show stereoisomerism, okay, here you may need to write down the structure. So it's really important that whenever you can visualize a structure in a question, do that, because this notice it's a little bit confusing. Okay, so those are type of questions that you can expect. Other type of questions that are very, very nice are like reaction flows or flows of mechanisms where you have to actually complete them. So actually I wanted to show this because you have it in exam papers. This is from OCR, a past paper, but you could also summarize all of the conversion between functional groups in this way. Okay, so I would highly suggest you to try this. So if you would like to try one of this, just to give an introduction, I would highly recommend you to try this one because you really need to get drawing. So why don't you stop the video and pause it whenever you're ready to hear the solution? So maybe first you could think about the justification of, wait, why wouldn't it have a stereoisomer? Okay. But also it's, yeah, an isomer. Okay, so isomer would be, remember, it could be any type of isomer. In this case, aldehyde, they are functional group isomers with carboxylic acid, with ketones, because you can really just say the carbonyl and move it around. Okay, but if it doesn't show stereoisomerism, it's because, so you have 1, 2, 3, 4, 5. So this is my aldehyde. Okay, this would show stereoisomerism because it would form a chiral center. However, if you have a symmetric ketone, the product of that would be, and I'm going to write it just like this so you can really visualize how it's the same as this chain. It has a chiral center. Sorry, it doesn't have a chiral center because notice that it's symmetric. So what would be the justification? So you have just one marker for the structure of it. Remember the stereoisomers. So the actually is the product that is required. So this would be your mark. And then the justification would be, well, simply because it doesn't contain and keyword here, chiral center. If you miss the word and you explain because it contains the same groups around the carbon, or it's symmetrical, or it's carbon attached is not attached for different things, it would still be marked. Okay, so as you can see, this is where you need also a bit of interpretation and not only knowledge of the stereoisomerism. Okay, so we've actually, during the course of the lesson, I have talked and I have explained things to you exactly in the way that the mark scheme wants, you know, these answers. So I'm just gonna say them one more time. I'll let you read this first two, and then I will tell you the solutions, really focusing on the mark scheme and the mark distribution. So let's read the first one. So the only way to distinguish between stereoisomers is the plane of polarized light. So one mark would be which would the instrument to use, which is plane of polarized light. And how are they different? Well, because one rotates, like, or you could say that it rotates, rotates the light in opposite directions. 2 marks. Let's read the next one. Explain why the reaction produces a racemic mixture. 3 marks. And here I've explained it very clearly before. These 3 marks are: carbonyl is planar, so there is equal chance or equal probability of attack from either side or from above and below the plane. Very good. The 3 very clear marks. Easy to get, once you know how to explain it. Thank you for joining this lesson, and please check my website for all of the information, and otherwise you can write me directly for any help.